Hello everybody and welcome to the talk entitled Stochastic Contextual Dueling Bandits under Linear Stochastic Transitivity Models. This is a joint work between me, ViktorBengs, and Adirupa Saha and Eike Hüllermeier. So we consider the contextual dueling bandit setting, which comprises of n many arms representing choice options. We have a time period consisting of discrete time steps, one to capitalize T, and in each time step T the following happens. The learner observes some decision-relevant context information, so context vectors for the arms, and based on these, the learner selects two arms for the duel, so for pairwise comparison between the two arms, and also observes in return only preference-based feedback, which of the arm is more preferred than the other. And because this is a stochastic setting, we assume that these observations are noisy, so they are generated by some preference probability. And as we have here a contextual setting, these probabilities and the context information are related to each other. So depending on the context, we have a different distribution here. And as usual, the learner suffers regret if not the best choices made, which in the dueling bandit setting means that not the two best arms are used in the pairwise comparison. And then the crucial question is, of course, how to choose these two arms, which gives rise to the well-known exploitation trade-off in bandits. And in our paper, we generalized the existing modeling assumptions on these preference probabilities in the sense that we have considered the CoLST model, which is a more general model than the ones used before. And what is a CoLST model? Well, a CoLST model is assuming that each of these objects, so arms in our case, are associated with latent utility function, where we assume that we have linearity in the context with some unknown weight parameter theta, and these utilities are having distributions, so they are perturbed by a perturbation distribution, all IID, these noise variables, epsilon y till epsilon n, and this perturbation distribution G is associated with the function f we saw before, in the sense that the difference between the noise variables evaluated at some point z is f of z. And then the preferences we obtain are just given by the probability that one utility is larger than the other. And this is where this f stems from. And for this setting, we suggested the CoLSTIM imitator, which has as an input parameter a perturbation distribution G, ideally the one we have for the underlying CoLST model. And then it proceeds by estimating the weight parameter via maximum likelihood estimation. Then we draw n many random variables, perturbation random variables for the arms. We multiply these random variables with the confidence lengths we have in the estimation of the theta, and then we put them together to obtain perturbed estimated utilities. So we add to the estimated utilities this perturbation random variables weighted by the confidence lengths. And then we choose for the first arm the one which has the highest perturbed estimated utility, and for the second the toughest opponent of this first arm. And this mechanism is essentially mimicking the sorting behavior of a CoLST model. And the first arm and the second arm choice is tailored to make regret as low as possible. So this is a technical thing we introduced there. And in our analysis, we have shown that if we use the maximum likelihood estimation for the theta estimation, and also assuming typical assumption for contextual bandits, and we assume that the perturbation distribution we choose is the same as for the underlying CoLST model, then we have a cumulative regret for the suggested algorithm of square root t times log t times the dimensionality of the context vectors, of the weight parameter. And if we make a bit more stronger assumption on the Gram matrix underlying in the maximum likelihood estimation, then we get an improvement of square root d factor in the cumulative regret. And previous results have shown that this is corresponding then to the lower bound, to the minimax lower bound we can obtain. So we have here near optimality. And in our experiments, we also have shown that our algorithm is performing quite well, and it has also computational advantages over other existing methods.